This PowerPoint is on VSEPR theory, molecular geometry. Molecules have shapes, and the shape of a molecule is very important because it plays a role in the reactivity. So we're very interested in knowing what the shapes are. And what we do is we can use Lewis structures, and we can count something called electron domains, and from that we can predict the shape. And here are some examples of different shapes. Alright, so we need to be able to define an electron domain. An electron domain is the region of space that's taken up by an electron pair. A lone pair counts as one electron domain, and a bond, whether it's a single bond, double bond, or triple bond, also counts as an electron domain. Note that in a double or triple bond, all the electrons are shared between those two atoms, and therefore they count as one electron domain. So here's an example of a molecule, AB3, and the central atom in this molecule has 4 electron domains. There's one here, one there, one there. Those are all bond domains. And down here we have an electron pair, which is a lone pair domain. And remember that we're only counting electron domains around the central atom. We can also define the bond angle. If we draw lines through the nuclei, as we see here, the bond angle is the angle formed by the two lines. Alright, so what determines the shape of a molecule? First of all, each electron domain around the central atom adds to the shape. Secondly, electron domains want to be as far apart as possible. So electron pairs, whether they're in a bond or a lone pair, repel each other. And this is called VSEPR theory, valence shell electron pair repulsion. There are only 5 basic shapes, and we call these the electron domain geometries. We're going to go through each of the electron domain geometries. Now, the electron domain geometry depends on the number of electron domains around the central atom. So if we have 2 electron domains, as in this example here, then to get them as far apart as possible, they're on opposite sides of the central atom. So here we have the central atom, and we have 2 electron domains on opposite sides. The geometry is called linear, and the bond angle is 180 degrees. If we have 3 electron domains, to get them as far apart as possible, they form a triangle shape, and we call that trigonal planar, meaning a flat triangle, and the bond angles are 120 degrees. If we have 4 electron domains, remember that we have all of 3-dimensional space to work in. Instead of putting them into a square shape, we put them into what's called a tetrahedral shape, and the bond angle is 109.5 degrees. With 5 electron domains, the shape is called trigonal bipyramidal, meaning we have 2 pyramids with a triangular base. So trigonal bipyramidal. And the bond angles are 120 degrees for the triangle part and 90 degrees, shown here, for the bipyramidal part. The last electron domain geometry has 6 electron domains, and the shape is octahedral. All of the bond angles are 90 degrees. When we're finding the electron domain geometry, all we have to do is count the number of electron domains in the Lewis structure, and that's the number of electron domains around the central atom, and the geometry is the one that corresponds to that number of electron domains. So for example, here we have ammonia, and this is the Lewis structure of it, and from this Lewis structure we can predict the geometry, which is shown here. That is trigonal pyramidal. Now the thing is that the electron domain geometry is often not the shape of the molecule. So here's the electron domain geometry here. The molecular geometry is determined only by the atoms in the molecules, not the lone pairs. While the electron domain geometry is here, forming a tetrahedral shape, the molecular geometry only counts the atoms, which are shown here. It gives us a trigonal pyramidal shape. So let's look at how we've determined the molecular geometry. First thing is we draw the Lewis structure. And so you still have to know how to make a proper Lewis structure. Then you count the number of electron domains around the central atom. You have to count the number of bond domains and the number of lone pairs. And then we use the table to determine the shape and the bond angles. So here are molecular geometries. Now if we have two electron domains, they're all bonding, or non-bonding, so the geometry is linear and the angle is 180 degrees. If we have three electron domains and they're all bonding, then what we have is a trigonal planar geometry, shown here, and the bond angle is 120 degrees. If we still have three electron domains, two of them are bonding, one is non-bonding, then the geometry is called bent. You can see that this lone pair still takes up space, so it can't be linear. So therefore it has to be a bent geometry. Note, if there are only two atoms in the molecule will be linear no matter what the electron domains are. If we have four electron domains, all four of them are bonding, then the molecular geometry is tetrahedral. If we have three bonding domains and one non-bonding, as we have here, then it's trigonal pyramidal. And if we have two bonding domains, two non-bonding, then the geometry is bent. These blue balloon-looking things here are the lone pairs, and then we have the atoms there. If we have five electron domains, when the electron domain geometry is trigonal bipyramidal, there are two distinct positions. There's the axial positions, that's these here, and then we have the equatorial, and the equatorial are in the form of a triangle, and the bond angles in the equatorial are 120 degrees. The bond angles in the axial are all 90 degrees. So when we have lone pairs in this, the energy is lower when the lone pairs are in the equatorial rather than the axial position. So you'll see that as we look at the molecular geometries. So these are the molecular geometries when we have five electron domains. If they're all bonding, then it's trigonal bipyramidal. If we have four bonding domain and one lone pair, then we have a seesaw shape. If we have three bonding domains, two lone pairs, it's T-shaped, and you can see the T-shape here. And if we have two bonding and three non-bonding, then it becomes linear again. The molecular geometry when we have six electron domains, we have three possibilities. If we have six of them all bonding, then the geometry is octahedral. If we have five bonding domains and one lone pair, it is square pyramidal. And if we have four bonds and two lone pairs, then it is square planar. Okay, now as far as bond angles go, lone pairs take up more space. They're physically larger than bonding pairs, and that changes the bond angle slightly. For example, here on the left we have methane, CH4. It's tetrahedral shape and the bond angles are all 109.5. If we look at ammonia in the middle, that has three bonding domains and one lone pair, and that lone pair pushes the hydrogens closer together, which makes the bond angle 107 degrees. For water, where we have two bonding domains and two lone pairs, we have two lone pairs pushing those two hydrogens even closer together. Now, I don't expect you to know those particular numbers. I expect you to know 109.5, but as we get more and more lone pairs, I do want you to know that the atoms become closer together. So instead of 109.5, it would be less than 109.5. Multiple bonds are also more repulsive than single bonds, so they affect the bond angle. So for example, with this molecule here, you can see where the double bond is. It is pushing the two chlorines a little bit closer together, and instead of all of the bonds being 120 degrees, we have the two between the oxygen and chlorine being larger than 120 degrees, and the bond angle between the two chlorines being less.